Good morning. It is a bright, warm, sunny March day, and we have just arrived at the Space-Comm exhibition. So what's the sustainable engineering team going to be hoping to achieve today? Well, there's the show. Here we are, and we are looking for technologies for our audience and our readers to be able to design into their new products to reduce their environmental impact and improve their performance. So we are going to be looking for technologies that are lightweight, that are integrated, that are reliable, that are durable, and very energy efficient. So into the show we go, and at the end of this, we'll be coming out with a whole raft of interviews, boots on the ground, taking a good detailed look at these technologies and how they can potentially be applied to your design projects. Okay, as you can see, we are on the Micron stand, and I'm with Daniel Goodwin. And what we're looking at here is the introduction of a new portfolio of space-grade memory product. And how that portfolio is designed, manufactured, and delivered is a fascinating process. And I'm going to ask Daniel just to walk us through how you're going to be delivering that portfolio, what it's going to comprise, and maybe some of the technical bits that we were just talking about in terms of wafer level kind of technology. So Daniel, over to you.
Sure, John. So right now what Micron's doing is we're rolling out a space portfolio of NAND, NOR, and DRAM products. We're taking our commercial grade product and we're running it through radiation testing to get the characterization data, and then we're screening it through the NASA PEMS INST2, which is the standard to screen for traditional space products. That will end up reducing two lines of products, one a traditional space product at a higher price point for those that need that, and then there will be a commercial space product that we're still in the process of defining that will come with the radiation characterization data, but at a lower price point that meets what the commercial new space customers want to do. But to the other question is, what we're doing with like that right now, it's starting with a high-grade automotive product, but we're taking our lessons learned and we're reading that back into the factory to do what we currently do, which is kind of unique to Micron, and what people don't know is at the wafer level, we have learned over 4 decades of development what parameters matter for different industry use cases. So we will segment the wafer today for automotive purposes, which is higher or lower temperatures, or industrial purposes or commercial purposes. We tier and grade the wafer at the wafer level before it's sent off for assembly and test. We're taking those same lessons learned from the radiation testing, and we plan on doing that at the wafer level, so that we will start with our space portfolio with a higher grade product that we know will survive better, and we will increase the performance for TID, a single event effect, and the things that we're testing for and that the customer cares for in space. So it will be form, fit, function the same across the whole product line under a part number, but the performance characteristics for the end use cases will be different because of that tiering and testing that we do during the manufacturing process. Does that make sense?
It does. That's absolutely fascinating. I had no comprehension that that process even existed.
Yes.
So I said, and you were mentioning there's a kind of bell curve to this industry. We're coming out of automotive with that type of spec into sort of low Earth orbit type applications, and then going out into more demanding applications.
Yeah, what I was describing there is we know very well that the traditional space market defined by NASA and ECSS in Europe, very well understood. The requirements are very well defined. This commercial space market is not well defined, and each customer kind of has a different view. Right. Is it NASA light, or is it commercial plus, or is it so? What we're trying to do for that market is figure out the price point, the testing, and the stringent criteria within a bell curve where we can hit 80% of the market that's looking for that for the commercial space customers, because it really internationally is not well defined what commercial space is looking for.
Brilliant. Okay, just to conclude, what's the total time scale for these products to arrive in distribution and ready for sale?
So we currently have a 256 gigabit NAND ready for sale today for long-term storage. It's already been flown for solid-state drives, space data recorders. We have a 1 terabit NAND device that is completed testing for radiation. That will be screened and ready for sale, I believe, by third quarter of this year. And then the DRAM products, we're starting DDR4, LP, low power DDR5 and DDR5. Those will come out kind of in that order starting in early 2027 for the traditional space market, and the new space market will come out as soon as we've kind of defined that bell curve I was describing.
Brilliant, perfect. So we'll see you back here next year with your full portfolio in place, probably, and hopefully some case studies.
Yes, sir.
Yeah, brilliant. Excellent. Thank you for your time.
Thank you. Thanks, John.
Right, so we are now on the Solsta stand at Space-Comm 2026, and we've stopped by to have a look at this VPT product. It is a DC to DC converter, and what's special about this is specifically designed for new space. And so I'm here with product and technology expert Tom Freeman, and Tom is going to talk us through the attributes of this product, how it's designed, what its technical specifications are, and how that suits the new space environment. Yeah. So Tom, over to you.
So maybe I should start with where we were historically, and then kind of move through. So what we've got on the right here is kind of a traditional fixed film hybrid part. So these are ultra reliable construction. What would have been used on the shuttle or something like that. It's designed for systems that must not fail, right? And so they go through an immense amount of screening. They're using radiation tested, lot accepted parts. They go through months and months of heat soak testing and full electrical load testing. But the problem with that is it's very, very, very expensive, right? And so for in a world where we're launching thousands and thousands of satellites a year instead of maybe 10 or 20 or 100, that kind of product doesn't suit those kind of applications. So you need something else, a different paradigm. And that's where these new space grade parts from VPT are coming in. Okay. So instead of using these steel can constructions, it's a plastic package. And that saves on weight and it saves on cost. And they're also using a different construction internally. So it's still a radiation tested part. It's still approved for radiation performance in space. But they've set it at such a level that they're not using like the most expensive possible grade of components, right? They've cost optimized it. And so they've set a radiation tolerance at about 30 kRad, because that's going to get you 5 to 7 years of lifetime in low Earth orbit, right? And they've set the single event level at 42 MeV, and that's because in low Earth orbit there's basically an ion need for the amount of energy that the incoming particles are going to have. And beyond that 42 MeV point, you really need to be way up at like 85 or plus. Right. So it's the cost-optimized solution for that. And the reason they have to do that is because if it fails, if the power components fail, it can take the whole rest of the system out with it, right? Because this high-voltage spike comes through from an unexpected, high-energy particle hitting the system, and it'll just kill everything. The whole satellite will just die instantly. So you need something that's going to survive that and not kill the whole system, right? But it also can't be that expensive. It's got to be so. VPT are bringing these parts to the market. We've already had a great deal of success. We're winning designs all over the place with this. And it's bringing a factor of 10 reduction in cost compared to traditional parts. It's a real game changer for them. And they're expanding the range at the moment. They've just released the point of load part there, you'll see. So that's brand new to this show. It hasn't been exhibited anywhere else before. So they're really moving this product line and this technology forwards to help meet the demands of kind of the rapidly expanding space market.
Okay. I can see different sizes and configurations. That's relating to power handling, voltage, current. What?
So they're all different power ratings. So it's actually a very easy naming scheme. So the VSC, you see the VSC 30 there. That's a 30 watt part, and the VSC 15 is a 15 watt part, and then you've got the VSC 100 and the VSC 5 down there. That's a 100 watt and a 5 watt part.
Okay.
And you can configure these in multiple different blocks together off the same filter. So you can have multiple different voltage rails, or you can have multiple blocks working together in parallel. So if you need like 400 watts of power, you can use 4 of the 100 watt converters and bunch them together, and they've got sharing pins so that they won't cause nasty EMI effects between them. So it's a really well thought out product, and it's designed to be as easy for people to use and implement into their systems as possible.
And with any DC to DC converter, efficiency, I guess, is something. How do they look on efficiencies?
So these are around 80 to 90% efficient. So they're silicon based. They're not GaN. We've got GaN parts in the pipeline, but they're not ready yet. No. GaN is we've got one example of the GaN part. So you see there the SGRB. That's like a real high-end 1600 watt. It's designed for geostationary orbit. So that's like the absolute top end of the worst possible environment that you can put electronics in.
Yes.
And so those are like the absolute top ends, and they're commensurately quite expensive because of the amount of testing and engineering that goes into them. But GaN will be coming. Okay. It's coming.
So maybe see you here next year with some GaN parts?
Maybe.
And one final just practical thing in terms of sort of pinouts, footprints, that sort of thing. Anything special there? Or?
It's all very standard pinouts. It's all available. They're designed to be interoperable across the product line. So you can use the 10 amp filter there, and you can match it with 2 or 3 different parts. It doesn't matter. They're all designed to match together well and be as easy as possible to use, right? You don't want extra complexity if you can avoid it.
Yeah, brilliant. Well, that's excellent. A lot of the conversations we've had here today have been about the new space environment and the different requirements and regulations and certifications, that sort of thing. This clearly is optimized to fit into that space. So we look forward to following this technology, and in particular maybe get some case studies in the future and see how they're actually being used. So we'll be back in touch.
Brilliant.
Thank you for your time.
Thank you.
So we are now on the Amphenol stand, and I am with Jean-Baptiste, and we are looking at high voltage connectors for applications in aerospace. And what caught our attention was the Raptor, this particular product here. And this is all part of the move to electrify the aerospace industry. What we're looking at here are voltages. I think we spoke 1,000 volts on this at 30,000 feet. So there we're looking at, obviously, battery drive systems. So electric motors, battery packs, hybrid as well, I guess. And I was just going to get Jean-Baptiste to talk us through maybe the construction and design of this product. It's relatively new, I think. It's a new technology, bespoke to yourselves, allowing you to deliver those very high voltages at altitude without insulation breakdown, without arcing and that type of thing. So please talk us through.
Yes. So this is called a Raptor connector that we have developed, finalized to develop it in 2022. We've designed it specifically for high power application in aerospace, as you said. So this connector is a single pole circular connector. Basically, that can be, as you said, can be used in electric engine for hybrid and full electric engine. So this connector is basically, I'll try to open it. So it's our own design, okay. And we have designed the whole connector, and especially I will try to open it softly. There we go. So we have the back shell here, and the insulator, right, that is protecting the conductor. And this is our conductor that we have developed specifically. So this specifically for the Raptor connector. So it's called the Talon contact. Okay. So it is a silver plate copper connector, copper conductor. Sorry, with silver plating over it. So yeah, this connector is very interesting for this market. So we don't have. We have a lot of interest from our customers, so but all the major customers, all the major engine manufacturers, or the new one as well, so all the new startups that have been developed over the years, specifically for the electrification of the aerospace market.
Yeah, sure. The conductor there, it's a crimped assembly, direct to cable, yeah.
So yeah, this is a contact that will mate with the other part of the connector. So this is called a receptacle, and this is called a plug connector. Okay. So this here, the receptacle is locked into a box normally with a bus bar termination. So normally you can have here the screw with a lock here to block to help create the contact with the system behind. And then you plug your mate your connector like that. And this part here, as you said, so it's a crimp. So you have the cable on this side, and you print the connector with the cable, and then you put it back on together, and then the connection is done.
And you say that the insulation is a critical component to this design for the voltage at altitude.
Yes.
Yeah.
So we have developed specifically, we have designed specifically this connector to be resistant to partial discharge in altitude. So yeah, the insulator here is critical for this application. Yes.
So when an OEM's looking at electrification in an aerospace environment, the two critical bits of information you need for this specification is essentially maximum voltage, maximum altitude, and then from those two you can start to work out which sort of grade of connector you would need. Yeah.
Yes, that's exactly that. To summarize, that's exactly that. So there are also other parts. So it can be the temperature, the environmental temperature, the current they need for the application, and other things. So the size they need, the weight they are looking for, and so on. So there are a lot of things, but basically the first question we ask is altitude, maximum voltage, and current location.
Excellent. Well, thank you very much, Jean-Baptiste. We're seeing a lot of case studies at the moment coming through the magazine and website about test flights of electric and hybrid aircraft. And so I guess if you're in the OEM sector, manufacturing those types of airframes and the like, then if you're looking for power connectors, come and talk to Jean-Baptiste at Amphenol. Okay, right, we are now on the Celestia stand. I'm with Malachy, and this caught our attention as we were walking past this stand, so we thought we'd drop by and see what this is all about. This is all about phased array antennas. So with all the constellations of satellites heading up into space, they need to communicate back and forth with the Earth, and that would normally be done with a traditional satellite dish. Problem is the numbers are getting, as the numbers rise, so does the demand for satellite dishes, which is all about material, installation, real estate, land, etc., etc. This is a solution. This is I think I would be safe to say, a kind of software-defined dish.
Yes.
Yeah. And what I'm going to do is, it's a fascinating technology. I'm going to ask Malachy to explain exactly how it works, what the benefits are, the sort of sustainability benefits in less land use, less material, etc. And then I think you've got a sample of an actual phased array antenna that we can have a closer look at to see how it all works. So Malachy, over to you.
Okay, thank you. As said previously, normally we communicate with satellites through satellite dishes. One thing about a satellite dish, it talks to one satellite at a time. It's the way it works. It's like a mirror that points to the satellite. So because we're putting up more satellites, we need to put more and more dishes on the ground to be able to talk to all the satellites that we have. And as you know, we've moved from about putting 50 satellites a year up to now it's like approaching 3,000 a year that we actually put up. So it means that we'll need to have a satellite dish. If you want to talk to those additional satellites, you need to expand the capability on the ground. And currently the way we do that is we put more and more satellite dishes. And how it's done at the moment, you would have a field that may have 10, 20, 30, 40, whatever you need. But as we put up more satellites, we need to actually clear more real estate and populate that with more dishes. So what we've done here is looked at the dish, which is like a 60-year-old solution. Still works, there's nothing wrong with it, but how do we scale up in a sustainable way the ground segment? And this is where we looked at electronic antennas. Now, they've been around for a while in different applications, and what we've done is look at the phased arrays, which is different. It's software controlled, it's all controlled with software, and it's done in a clever way of manipulating lots of tiny antennas. So if I show you something, an example of one that we have, what this here, this is just one part of a larger antenna, and this is actually consists of 256 individual small antennas, which you'll recognize with each of those little squares that's on that example here. And what we do here is we are able to manipulate how each of those little antennas work together, and that's where we change the phase of each of these, and hence phased array antennas. And by manipulating that, we can actually concentrate the RF energy and point it at the direction of the satellite. And the satellites, they move in space, so we are able to track the satellite and keep the communications going as it moves across. And this can be manipulated with software. In fact, we can follow multiple satellites with this, and so they're all tracking it across the sky. And so if you can imagine a large field with multiple dishes, we can replace 28 of those dishes with a unit this size, which is roughly about 5 meters by 5 meters. So where you would normally have one dish, we can put 28. And the other aspect to it is normally this is out in a rural setting, because if you need that large real estate, so we can make it small enough that it actually fits on the roof of like a data center.
Yep.
And you don't need any of that additional real estate, and you can do a direct connection where your infrastructure and everything already is.
Wow. Brilliant. Thank you very much. It's interesting. I saw last week, I was talking to a friend of mine about who's involved in testing the concept of data centers in space.
Yes.
In terms of how they would be powered and cooled, etc.
Yes.
I imagine if that type of technology did migrate, then this type of technology would probably suit that quite nicely.
Well, I think in space, because you've got more satellites going up, there's more and more data happening.
Yep.
So having the data centers in space allows you to do some of the heavy lifting in orbit. So rather than sending raw data, do some initial analysis on there. It's like edge computing in space. But there's still a lot of data that we're creating, and how do we make sure we access it, either the direct raw data, or how do we get this, let's say, pre-processed data down as well. So being able to provide more and more bandwidth, then that's where it goes. The ground segment has to scale to match how we're scaling up satellites.
Brilliant. Well, there it is. So, yeah, edge in space, phase array antennas, software control. It's how this industry is moving. Right, okay, here we are on the Jaltek stand, and I am with Chris Day, and we're looking at some real sustainability-focused printed circuit board technology. I'm going to whiz through. So this board here is for a solar farm in space. This board here interposes, dealing with obsolescence and component unavailability. This board here, fascinating. This is a combo of additive and subtractive manufacturing technology kind of real world leading stuff here. And this board here, which is all about regenerative power in automotive applications. So, Chris, if you can really quickly just give us a few seconds on each.
Yeah,
that'd be great.
So this was built as a proof of principle for beam steering electronically, and it's part of an initial system called Harrier. And we went from concept to live full demonstration in 8 months, which was brilliant, and that proves that we can point the beam wherever we want to, and power remote bases or remote villages, etc., that don't get electricity, etc. So that's really powerful. With these little interposers, it's designed so if you can't buy the component that normally sits on a board, but you can't get it in this package, but you can buy it in a different package, what you do is design a little interposer board, route out the signals from this one to this one, and then you replace the component that would have gone on the board with this, and then that sits down on the board.
Gotcha.
This is a fiber optic transceiver characterization card from a client, but the packages here are really, really tiny. So this has a 40 micron track and a 60 micron gap. Okay, so that's 0.075 of a millimeter tracks. You can't etch. So traditionally, when you make a circuit board, you would etch away the copper you don't want. You start with the solid mode copper and you etch it away. You can't do that with this because you can't etch lower than about 75 microns. So you have to add the copper with the really fine tracks on the first 2 layers, and the other 4 layers of the board are done conventionally with subtractive. Capability, unfortunately, is Chinese. I say that unfortunately because we really want that sovereign capability here. It's starting to come into Europe, but we're not advanced as they are yet. But there's a lot more to that. This is a part of very old, actually. It's about 15 years old, and it's part of the initial KERS system on a Lotus F1. And it was used in races, etc. So when you first started seeing KERS, which obviously now everybody has within their domestic cars, etc. It's one of those leading edge things. Pretty complex transceiver, transmitter on one side, receiver on the other. It was an ESA project that we did it for use on the International Space Station, and it's quite unusual. It's 14 layers with blind wire technology, which is very unusual to use in space because of the potential outgassing issues. But we constructed it and manufactured it in such a manner that was allowed. Radar control card, but that's a mixed technology. So you've got surface mount control electronics here. At this end, you've got cavities where you take a die, flip down and wire bond. So the dies will be flipped over, put into the holes. It's solid ground on the back. That sits down on a heat plate. And then you wire bond off of the dies onto the legs at multiple layers. And then that interfaces to the digital control circuitry. So you surface mount assemble that, but you have to wire bond that. So it uses what's called an any-pig finish. So there you go, that's an idea. And a CubeSat, which we've done the whole development for. Everything about it and launched it. So,
fantastic.
Okay, thank you very much.
Thank you very much, Chris.
Cheers. Thank you.
Right, I am now on the Ergodic stand, and I'm with Michaela Murphy. And a little bit of a deviation from the technology we've been looking at. We're now going to be talking about supply chain. I know a little bit about supply chain because I have been writing about it and in it for 25 years or so now. A lot of the decisions in the supply chain can be emotional reactions to events occurring or predicted. But we're moving into an AI era now where predictivity is entering a completely new phase. And that's where Ergodic is working. The idea of creating a world model, or world models, mapping that to reality and being able to make decisions more accurately and also more sustainably, I guess, in where products are sourced, how they're moved, etc., etc. So I'm now going to ask Michaela to give us a bit more detail on that and how people would get involved with this.
Yeah, of course. So John, you've hit it spot on. So Ergodic uses AI world models to build operational performance and sustainability simultaneously for performance rooted in responsibility, really. So we use these AI world models to run different simulations to be able to understand what could be happening in 6 weeks or 6 months to your supply chain to really become more proactive and resilient over time. And that could be for anyone who's a warehouse manager all the way up to C-suite, and we can curate the platform to any of those decision makers. So it really is talking about making smarter decisions now today for the future.
If I look back over the last sort of 20 or 30 years as to classic interruptions in supply chains, in the electronics industry, for example, we've got tariffs right now, but in the past we've had volcanoes, port strikes at ports, that sort of thing. You can cope with all of that type of stuff?
Yeah, so through having conversations with specific organizations, we can really map what's important to their internal supply chains as well as global events. So we can tell you if there's a hurricane coming to any of your factories or if there's a tariff that may be affecting you soon, so you can really see what's coming forward in the next future.
Well, to keep production lines running, to keep them efficient, to keep them sustainable, need nice steady flow of product in and product out. So we'll be keeping an eye on you guys, see how things go, and best of all, would be able to come back and maybe do a case study in the industrial sector and see how it's actually working.
Yeah, of course.
Cool. Excellent. Thank you for your time.
Thank you so much.
Okay, right. I am now on the Cinch stand, company I know well, and I am here with Jerry. And what's caught our attention is Synapse technology. It's an interconnect, solderless, compression-based, using these wire bundles as connectors. And I'm going to ask Jerry, what sort of problems or challenges would engineers be facing for this to be the right solution with a sustainability angle in terms of reliability, recovery, etc. So, Jerry, talk us through this technology.
So the Synapse technology enables engineers to reduce the weight, the bulk of their solution. It enables them to increase the performance levels. It de-risks the manufacturing at their level of the part because it's solderless. Yep. So you know, if a mistake is made, it can be reversed easily and components recovered. It's highly tolerant of shock and vibration, 20 Gs of vibration, 100 Gs of shock. It typically has higher temperature tolerances than many other interconnect solutions. It's a far lower profile. In terms of sustainability, as we know in the space industry, every gram of weight that you want to put in orbit is extremely expensive. Yep. So our customers are very interested in reducing, mass and package size. And should there be any issues with faults found on their equipment, it's easy to recover the parts and replace the parts.
Okay. You showed me some examples. I think you had some sets behind there of the kind of magnitude that this product can go through, from tiny little interconnects all the way through to these large sort of land grid array parts here. I'm seeing ASICs being referenced. Maybe you could just show us a couple of those examples.
Here's some examples. These are all deployed within the space industry. Some are for land grid arrays, such as these designs, where we not only provide the connection points, but also the chip holding within the device. That's then compressed.
Right.
You can also have combined signal contacts, which will take 1 to 3 amps, and these larger contacts at the end of typically for power, so 5 to 10 amps. You can marry up RF arrays, signal arrays, power buttons, all within the same device. The size of the device you can make is very, very scalable, from some of the larger devices here to some of the very small devices, which effectively are arrays the size of that RF array there. The RF array in itself will take 50 gigahertz speeds. We've got white papers on our website with our test data demonstrating that. So it's a very, very versatile technology applicable to pretty much any shape, size, marrying up with flex circuits, as you see in this example here. Usually use interposers, as is its main use. And it's a tried and tested technology. This is a NASA technology ready boost level 9.
Oh, okay.
So it's in space, it's on Mars.
Right.
Yes.
Oh, okay.
Yeah. And it's proving very popular at this show, I have to say.
Yeah.
When our engineering customers see this, you almost see the light bulb coming on.
Yeah.
And they can see the solutions, the problems they can solve with a solution.
Yes.
This is all homemade in workshop in the UK.
Oh, fantastic. Excellent. Well, thanks very much, Jerry. If you look at our pillars of sustainable design, this is covering multiples of those. So we're talking about integration, minimization, weight reduction, reliability, durability, recyclability, scrap reduction, reuse, and on some of these circuit boards, just the financial value of one of those devices, maybe an ASIC or an FPGA type device of that scale, that's big money. So, yeah, vibration resistance, temperature tolerance, pretty much covering everything.
Yeah. The assurance of quality for the customer's assemblies. They want to know that when they build them, they're going to work. Because once you're up there, you can't service them. And once installed, this technology simply does not fail. It can't. Yeah. Physically impossible to fail. Yeah.
Great. Well, thank you very much for your time, Jerry. And I think our readers will be, or viewers will be very interested in this technology. And we'll be coming back to you, maybe get some case studies as well.
Yeah. Cool. Okay, nice to meet you, John.